My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, good morning to you all. So it's our 206th International Physics webinar. As you know that we are staying in a corona pandemic situation, so it's very difficult for us to continue our normal academic program inside the campus. We have to start our online program. So we are trying to adjust with this new normal situation. So I think you have already come to know that we are trying to make an environment for our students so that they can interact with physicists from all over the world and learn a lot of things. So today we'd like to welcome you all to a joint session between SN Bose National Center for Basic Sciences and our Department of Physics and Pabna University of Science and Technology. And we have with us here today Dr. Priya Mahadevan, Madam, Senior Professor, SN Bose National Center for Basic Sciences, Kolkata, India. And she also connected with us, so I'd like to welcome our speaker. So, Madam, good morning, and thanks for accepting our invitation. Before going to you, I'd like to introduce you with all of our students and viewers. So, I think dear viewers and students, you have already come to know the title of the Students International Physics webinar. Title is the Building Solids Layer by Layer, a route to tune their properties. And our speaker is Dr. Priya Mahadevan, Madam, FASc, Senior Professor, SN Bose National Center for Basic Sciences, Kolkata, India. And if we see her academic and professional career, you can see Dr. Priya Mahadevan, Madam, completed her Master of Science from the Department of Physics, IISc, Bangalore in 1993, and her PhD from the same department in 1998. And we can see she got several awards and professional activities. And membership. She worked as an editorial advisory board member at the SCS Energy Letters from 2021 to 2023, and M advisory editorial board member from 2021 to up to 2025, and member of IUPAP Commission on Computational Physics since 2015 still continue, and MRSI Medal 2015, elected fellow of the Indian Academy of Sciences in 2014, DE Raja Ramana Prize lecturer in physics for 2013, and other also. And you can see her professional background. She has started his professional career as a postdoctoral fellow at Tsukuba in Japan, and then she got another postdoctoral fellow in US also, National Renewable Energy Lab, Denver, USA, and then she joined as an assistant professor at the IIT Madras, Chennai, India, and then she changed her position, and she joined as a reader at the SN Bose National Center for Basic Sciences in 2005, and now she's working at the same place as a professor and continue doing. And she works in different types of research field, and the main area of her research is electronic, magnetic, structural, optical, and mechanical properties of system at nanoscale, and change orbital and magnetic ordering in P and D band system, models for magnetism and transition metal compounds, dilute magnetic semiconductors, and calculation of various spectral functions. So thanks for all of your patience. I think you will enjoy this session. So, Madam, I'd like to welcome you again. It's your time, Madam. You can start your session.
Yeah, thank you very much, Dr. Das, for the nice introduction and also the invitation to talk about some of the work which we have been doing recently. As you can see from the title, I'm going to start by talking about how one can tune the properties of materials when we can build solids layer by layer. Of course, the idea of building solids layer by layer is not something very recent. This was something which started, which actually every electronic device that you see around you is based on this kind of technology, where people started out with semiconductors and, they started growing a few monolayers and, heterostructures basically few layers of one material, few layers of another material, and tried to control their properties and tried to bring about, and that is what modern day electronics is based on. However, what I'm going to talk about is another class of materials. As I've heard that most of you are from a bachelor's background, so what you will know is that in a solid, you could have, like when you allow, you could have different types of bonding. You could have covalent interactions, like all the semiconductors that I just spoke of belong to that class of materials, where each layer is interacting via covalent interactions with the layer beneath. However, has been in a different materials. This field related with the of graphene, basically experiment which any of you could do even in your, at your house, is to take a piece of sellotape or a piece of Scotch Brite, put it on this class of materials, and and just stick it and then put it on this class of materials, and just when you, for instance, a sellotape, if you just pull it out, would pull out a few layers of the material. Of course, this is obviously not possible with every material, and the unique distinction these materials have is because the materials belong to a class where the interaction between the layers is van der Waals type. I'll just go on to explain what exactly I mean by that. And the question is, how exactly can I manipulate the properties? And this is an important area in the forefront of condensed matter research today. And I'll just give you a glimpse of how exactly one is able to do this tuning. So now, before I go on to that, I'd just like to make a point that mostly whenever you study condensed matter, or whether you call it solid state physics, what you would see is that we always, any textbook example you deal with, always deals with periodic systems. And that's because we know how to work with, once you have a periodic system, you essentially are talking about an infinite lattice. But so you can just go from, you have a periodic arrangement in real space. So what you would have seen is that you always, brought about simplifications by going into the reciprocal space, which is nothing but the Fourier space of these. And then what you have to work with is you can just work with one unit cell in your reciprocal space, and then you can discuss various trends, generic trends that emerge in the properties of these materials. And of course, these are not possible in systems which are aperiodic, and usually that's the reason why we don't have this as a part of any standard, solid state physics course. But you do see a lot of, finite systems. Most of you would have at some point, at least on the internet, seen examples of nanocrystals of semiconductors. And what you can see on the left-hand side over here in this figure is, I've zoomed in onto one of these dots, which are dot array, which I have over here. And what you can see is that finite. There are atoms over there forming this thing called a quantum dot, and you have a finite number of atoms within this spherical region, which has a diameter of 5 nanometers. So you have these finite systems, and the question is that, can I still borrow all the ideas that I have for the infinite periodic systems and bring them over here and still talk in the same way? More recently, in textbook examples, what one felt was, if one could have, a large number of unit cells which were close enough, and there is, an interaction between them, some kind of coupling between them, okay, then you can still probably talk about band structure in these systems. So I'm going to take another such class of materials, which I will come to in a few minutes, and I'll bring a twist to the tale by the way I grow these materials. So I'm going to take a set of very traditional semiconductors, which have this. I'm going to take the example of molybdenum diselenide, though this some of the ideas that I'll be introducing here could be applicable to the to several of the family of these molybdenum transition metal dichalcogenides. So what you have here in the plane, what you can see over here is that, let me just get my pointer to work. Yeah. Okay. So what you can see over here is I have, when I look at it from top, what I have is that I have these transition metal atoms over here in these blue circles, and these are my selenium atoms. They seem to form a hexagonal lattice over here. And for those of you who've done some course in the basic course in solid state physics, basically, if I just took these two atoms over here, and repeated them by considering the vectors which form this structure, okay? If I repeated them through, I can generate the entire infinite lattice, okay? So that's so far so good. This is what it looks like from top. And then what I see is that if I used some method of mine and I calculated what its band dispersions were, what you can see is that you have, it's like any typical semiconductor example you have. That is, you have a set of occupied states over here, and you have a set of unoccupied states over here, which are separated by this which are separated by a band gap, which is indicated by this red arrow over here. So essentially, this just constitutes a textbook example of a semiconductor. But if I look at it, from the side, what I see is that these materials are slightly different. And what I can say is that I have this, whatever I showed you from the side is now looking like this. That is that you have the central layer, which has the transition metal atom. You have the top layer, which are the selenium atoms or whatever anions you have, and a bottom layer of this. So this, if you looked at from top, form this hexagonal lattice. And I can actually stack these layers, one on top of these of each other. And in contrast to the semiconductors, where we really had to be concerned about putting it directly on top of the atom of the lower layer, here one can relax that consideration, because the interaction between these layers is very weak van der Waals interactions. Okay, that happens because all the bonding considerations that I'm talking about are satisfied within each layer itself. Okay, so therefore, you can think of it as just like your inert gas. So inert gas, I mean, when you studied chemistry in high school, you would have heard of these, the octet filling rule. So by the time you come to the rare earth atoms, what you find is that what you would have studied in school would have been that they have the octet consideration, so they really don't form any they don't form any compounds. But later on, you would have heard that they do interact very weakly via van der Waals interaction with neighboring rare earth atom, inert gas atoms. And as a result, what you would find is that they form very weakly bonded solids. Okay, so this is the reason why you can just take a Scotch-Brite and just pull layers apart. And what was novel about the Nobel Prize winning work of Novoselov and Geim was that they placed it under a microscope, and they were able to see that in this case one was able to actually pull out just one monolayer of the material. Okay, so that was unusual. That was the novel aspect. Though people had known for a long time that with a piece of Scotch-Brite or a piece of sellotape, you were pulling out few layers of this category of materials. Okay, so now what I can do is, as I said, in contrast to normal semiconductor, epitaxy of covalent materials, where I have to make sure that whether whatever atom I add usually likes to sit on top of an atom of the lower layer, and so therefore it doesn't. If I'm trying to grow two different materials, the lower layer is imposing its lattice constant on whatever I grow on top. Whereas in this case, what we can do is something more unique, which is that one can actually, if you took one layer, and what is shown over here is the unit cell corresponding to one layer, and then I put another layer, again the same unit cell, but it's slightly rotated with respect to the lower layer, and I can make these kind of heterostructures. And then what would I expect? Does it really remain the same way? Does it have the same properties that I just showed you, which is just a boring semiconductor? Or can I tune its properties and get something more novel and interesting, which over here? The other aspect which you can immediately see, which I pointed out, is that in the previous case, I just needed a small, if you remember, I just needed that small box, which I described as the unit cell, to basically, I repeated that. I took the atoms, the two atoms which were in that box, and the vectors associated with the box, and then I could generate the whole lattice for you. However, in this case, what you can see is that I cannot, since this one is rotated with respect to the lower layer, I would be talking about much larger unit cells. And this actually depends on this angle by which I'm rotating the top layer and placing it on the lower layer. Okay. So now, basically, this was something which people did very recently, and it has appeared in this Nature Materials, where what they did was they created a structure like this, where they took one of these transition metal dichalcogenides, they took tungsten diselenide, 2 layers of these, and created a structure of this sort. Essentially, I will gloss over the details of this, because this is merely to be able to look at some of the transport properties of this. But what you can think of is that just these 2 layers have their units correspond to transition metal diselenide layers, just like in the same structure that I showed you just a few view graphs back. And the top layer is rotated with respect to the lower layer in these structures. Okay. So now this again belongs to the same tungsten is an atom which is just below the molybdenum atom in the periodic table. So nothing should change. It should be it should have very similar semiconducting properties. However, what they saw was something very, very strange. So this is, if this lowest example, lowest plot over here corresponds to the simple semiconductor, and what is plotted over here is the resistivity as a function of hole doping. So what you can think of is, as I showed you, you have your valence band over there, okay? And what you're doing is you are introducing, with that structure that I showed you, you can introduce an electric field and you can gate it. And so you can actually dope holes into the system, and that's what they did. So suppose it was in the unrotated limit, which is represented over here by what they call the Bernal stacking, which has a particular type of stacking. What you can see is that, well, if I had my Fermi level, which was in the gap, I would have a very high resistivity because it's a semiconductor. And as I introduce more and more holes into the system, my Fermi level is going to move into my valence band, and so I'm going to see metallic properties, and so the resistivity drops. And this is what it is. Well, but when you see that, you look at different structures, different angles of rotations that have been considered over here, and what you can see in these cases is that there's something more which is emerging. You have this same behavior at the low, almost in the semiconducting region. You have this high rise, and then you come down, and then it becomes metallic, and then again its resistivity increases, almost as if again it's becoming a semiconductor, and then again becomes in systems. You're seeing that as a function of hoping, what you're seeing is that it's a semiconductor, a metal, and then a semiconductor, and again back to metallic properties, which seem very, very surprising to expect. Typical textbook examples, which I'm reproducing over, tolerance band for the semiconductor, a conduction band for the semiconductor, and a band gap. You're just, you have a continuum of states over here. So I'm doing my here, and so always there's going to be a band at the Fermi level, and so I should expect metallic character, right? So I see in class of materials. If I this was actually put into a phase diagram over here by the same group, and what they saw was, well, okay, so as a function of temperature as well as hole doping concentration, what they found was if they color coded the resistivity according to this bar chart over here, you're going to have at low temperatures, you're going to see states which are zero resistance, almost like superconductor, but this hasn't been verified. And then you have, so essentially a metallic state which has very low resistivity or zero resistance, and then again insulator, and then again back to metallic transport at quite low temperatures. So why is this system behaving in this unusual way? And this is also reflected by these plots over here, which actually, you can see that depending on my hole concentration, the resistivity, if you've come across in your courses, if you've seen what the resistivity as a function of temperature looks like, these are typical behaviors for metallic cases, whereas over here you have this sudden rise, which is indicating that it has some kind of band gap associated with it, like a semiconductor. Okay. So fine. So then the question is, this kind of behavior we don't expect with this class of materials, and I will just gloss over this point because basically one would expect materials where the kind of picture, the band description that I showed you about, if you can think of a solid, you have a lot, you have 10 to the power of 23 electrons moving around. So the question is the band, I showed you a plot of an electronic, of the band dispersions for MOSE2, and what that was calculated assuming an independent electron approximation, which is effectively saying that if, I consider all the electrons around me to be actually creating an effective field, okay? And this single electron moves in this field. So effectively, I do not consider in this approximation, I'm not considering the interactions, the Coulomb interactions between the different electrons exactly, but I'm just saying that the rest of the electrons are actually creating an effective electric field, okay, which this electron sees and therefore interacts with that. Okay, so this kind of a picture loses out on strong electron-electron interactions. And so the question was, why is it that in these materials where this kind of a description worked, why do we need strong electron-electron correlation physics interactions in these materials? Okay. Also, as I pointed out earlier, what people thought was, well, depending on the angle of rotation, what you can have is that you can have some instances where you can really imagine that the unit cell that I can talk about really depends on the angle of rotation. I can, in some instances, have unit cells, and in some instances, not for every angle of rotation, I need not have commensurate unit cells. It could be incommensurate also. Also, what you can see over here is that you can have, depending on the angle of rotations, my unit cell size could vary. Okay, it could involve a few thousands of atoms. It could all involve 10,000 atoms. It all depends on the angle of rotation. And so therefore, the question, what people thought was, well, it's essentially behaving like, so if you think of it that your unit cell size is very, very large, that means your reciprocal space, which is, goes as 1 over your lattice. Suppose I'm talking about A as my lattice parameter in the unit, in your real space, then my reciprocal space would have dimensions of 1 over A. So if A is very, very large, you can think that my reciprocal space is going to be very, 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 very small. Okay. So they thought that one should actually view these as giant molecules. And that's the reason why, when it comes to the bulk solids, what they said was, we have to expect that actually what is happening is, you have like a big giant molecule. You're not talking about bands, you're talking about isolated levels which are emerging in these solids. Okay, and that's the reason why people said that there is no band structure to talk about, if you can think of it. I mean, this is so what they thought was that essentially we are talking about almost flat, dispersionless bands emerging, and that's the reason why we need to consider strong electron-electron interactions to talk about these systems. Okay, so the question is that, well, at this point, what we have seen from examining the literature is that for this, the basic idea that persisted at this point was that these materials, these twisted bilayers or twisted layers of these van der Waals heterostructures, should be actually viewed as a giant molecule with isolated levels. Okay, so far so good. So let's go with this understanding and re-examine some of these ideas and try to see whether we agree with it or not. Okay, so what we did was, okay, as I said, one knows very well that as I pointed out earlier, the most popular technique to separate out these layers involves a Scotch-Brite or a sellotape, implying that there's a very weak interaction between the layers. Okay, so now if that is the case, then it's also reflected in this effective single particle picture, which I use to calculate where the energy levels are for this system. And I do this for one layer of this material, which a monolayer, which consists, as I showed you earlier, of the central transition metal layer and the anions on either side. That is referred to as a monolayer, and a bilayer consists of two of these such entities. Okay, so if you look at these band structures, what you can see is that there's hardly any in most of the region, there's hardly any perturbation of the monolayer band structure, because I brought in the next layer and formed the bilayer, which is exactly what I'd expect, because whatever I'm talking about, being able to pull them apart, actually means that the electronic interactions between the two layers are quite small, and that has to reflect in its properties also. Okay, so if that is the case, then let me try to quantify it a little bit more and try to understand what exactly is happening. So if I did a thought experiment where I can construct the solid, and by what the approximations which one uses goes by the name of a tunnel. So what do you do over here? So basically what you do, where you have isolated atoms which have these isolated atomic levels associate them, and as I'm bringing two atoms closer and closer, what's going to happen is that the electron on this particular atom is going to see the and what do? I recover the monolayer band structure. So all changes that are happening, I have a control over that because I know what are the interactions. So even though, these are materials which are called van der Waals materials, there is small covalent interaction between the layers, but it's pretty small. Okay, and that is what is reflected over here, because if I switch off these interlayer interactions for the bilayer, what I recover is essentially the monolayer's energy eigenvalues. So that's so now I understand what exactly is determining the changes when I go from monolayer to bilayer, okay, in electronic structure. So now, before I go any further, what I should remind myself of basic emergent quantum mechanics, which is that whatever I do, I have to, all along I'm saying that the upper layer is acting as a perturbation to the bands of the lower layer. Okay, so I have to have a scheme where I should recover, where I should recover my unperturbed limit also in the band structure. So in that, what I do, a simple, what I mean is that if I took a cell of, say, in this case, I've taken gallium arsenide and just make some repeat units and construct a supercell of this over here. What I can see is that, and I plot the band dispersions along the supercell reciprocal lattice vectors. What I see is that I see many more bands emerging. Okay, and I also see that if I could talk about a width of the band, okay, so this band is very wide, whereas over here the topmost band has narrow width, and this was only this. But if I made it 100 times, I will actually which has no width at all. Okay. So, but that's not correct, because I was constructing a supercell and there is no perturbation over here. I should have a method of, just by saying that my unit cell dimensions have become, much, much larger. So my reciprocal space has shrunk, and therefore I come to a case where the band dispersions is not correct. I should recover the unperturbed limit of the band structure. Okay. Because there is, in this case, when I'm just constructing a supercell, I have no perturbation at all in the system. So ways I can go about this, I can find out what the perturbation is in this case, and add that to the unperturbed Hamiltonian. In every case, what is the go to several orders of theory, what exactly is my final, what are my final eigenstates? The other way of doing it is what we, because we have a method which for the final, if I were to project the final state onto my initial state, and if this, so the ones which are the eigenstates would get projected, and you would get, you would get unity over there, and those which are not the eigenstates of the primitive cell case or the unperturbed limit actually not contribute. So using this kind of an analysis, what we did the same thing for this kind of for this band structure, and remember there is no perturbation. So essentially what we do is we project the final states, the supercell states onto the unperturbed state corresponds to the primitive cell, recover the same result, which is what we should do, because if my perturbation is weak in this case, I can use this method to gauge how much are my eigenvalues over here. So well, okay. So now what we did was we did two test cases over here. We took one where we 3D atoms, which we 50 atoms, And this unit cell diameter 52 angstroms in each direction. So this is about 16 times the primitive cell. In this case, as you can see, what we should find is that we have a very large unit cell over here. So do we have flat, molecular-like levels? So what we did was we did exactly the same analysis that I just described. That is, we projected find the perturbed wave functions onto the unperturbed state. And in this, remember that it's not a perfect supercell. So there is some perturbation, but what it essentially says is and the thickness actually represents the cell K point, which I will, if I soups the primitive cell. Essentially, what I'm seeing is that the low energy band structure is very similar to what I have for the primitive cells, which indicates that the perturbation is quite small. It's that's forming, but instead, what is that perturbation is quite small, and I the okay. So is this for all systems? But we know that people have seen some other introduced at the degrees, 4 point something degrees. So we took one such an angle, which had similar number of atoms, 16, 26 atoms, and similar sized unit cell. Okay, so one thing you would see is that angles, there's something additionally which is coming in, and what is that is that you can see that over here you can, if this is the top view that I'm showing you, okay. And so I start over here with a configuration where the two layers have all atoms sitting on the lower layer atoms. And what you can see is over here in this region, I type of structures emerging with these types of stackings. What you can see is that what started out was with something like this, where the lower layer, if you can think of it, if you looked at it from the side, okay, and if you looked at it from top, it looked like this, whereas with is something like this, where you have what if you look at it from top, you have the anion sitting in the middle, and things are slightly displaced from each other. The two or the two cations and the anions are not on top of each other. Okay, you see over here, you have large patches, particular regions. What does it imply? This implies that if you looked at this particular configuration and on top of the anions sitting on top of each other over here, what you see is because the electrons over here are repelling the electrons over on this particular atom, and as a result, the two layers would like to stay further apart, and so the separation, which is measured by this distance over here of the outermost atoms in each layer, is about 3.8 angstroms over here. When I have this particular any of these this staggered kind of configurations, what I see is that, and what I see is that the repulsion is much reduced, and as a result, the separation is 2 angstroms. So when we looked at this, what we found essentially, when we looked at these structures, we found that over here, so in these two layers, actually, when we within our calculations can move the minimum energy configuration, we find that over here the separation between the layers, which I showed you was measured as the, the separation of the outermost atoms in each layer, came out to be 3.74 angstroms over here, whereas it came out to be about 3.2 angstroms over here. Okay, 3.2. So essentially, this was one difference which we found. And then again, we did the same analysis, which I've been talking about. Okay, and what do we see? There's something more something different. We do have these dispersing bands, which we see over here. Okay, and what we see when we zoom in over here, what we see are something very different, and which is, localized space, and it's split off from the rest of the bands over here. It has a very small width associated, which is 19 MeV, and and these are the remaining bands. So what does this mean for us? This means that so this is my highest occupied band over here, and if I were to hold up this system, I go from a semiconductor, then I have this metallic behavior, and then again I have semiconducting behavior, and then again finally again as it does this, I could have metallic, and so on and so forth. So therefore what we can show is that we can explain the experimental operation of successive insulator metal insulator that's seen in this material, and it's not because this undulations that has in structure. But I spoke about that in some regions the separation was 3.8 and nearly 3.8, and some other regions it was 3.2. It's not because of that, because even if we kept it fixed at something which is intermediate between these two values, what we found was that, well, you do have this kind of split off band forming over here. So what's the origin of this? One thing before I move on to try to understand what the origin of this could be, what I can immediately say is that it's not because large unit cell and the fact my K space becomes very small, because what you see is I've taken two very similar sized large unit cells. One has it and one doesn't have these split off bands. So there's something more which is happening over here. And as I said, I was talking about which actually controls this, which controls this interactions between the, and I showed you a picture. It's actually this hopping between the atoms of the two layers controls the electronic structure when I have the additional layer. But you can see that all of them seem to have, at least these two have very similar interlayer distances, because the hopping interaction, what you can see, you can understand this even qualitatively, that what I spoke about was that this model, the tight binding model, has these hopping matrix elements, and it depends on the separation between the two atoms. If they're closer, obviously the tendency to hop should be larger. Okay, so this exactly, so if you plot it as a function of the distances of the anions in the two outermost layers, what you can see is that this is similar, slightly different. We see it off band. So what we did was we looked at a profile of where the distances fall, and you can see that in both these cases, even at the small angle, we had fixed the separation between the layers. We have these are selenium distances, or you can you can extrapolate that to my hopping interaction strength seem to be concentrated in some regions, okay, in these two cases. Whereas when I had the other case which was the large angle, it seems to be randomly distributed through the unit cell. And so this actually this concentrated regions of large hopping interaction strengths actually leads to large perturbations in these regions, and leads to the what we find here of the subband formation. The strong perturbations in these regions leads to the subband formation, and this is possible for these small angles, whereas it's not possible in the large angles where we do not see, what I showed you in this picture is, you have these patches of different high symmetry stackings, which comes about in your low rotation angle structures, which is not there for the large rotation angle structures. Okay, and though this is not for the same system, there have been very recent experimental reports where these angle resolved photo emission experiments can actually, calculate, can determine experimentally the band dispersions for these materials, and they have taken twisted bilayer graphene. Okay, and what they have seen is that actually the rest of the band structure, it's not like an isolated molecule where you should see only flat bands right through, but what you see is that you have strongly dispersing bands right through, and then you have a flat band, split off from the rest of the bands emerging. Okay, with this, I'd just like to go on to the conclusion, because I think I've run out of time. And I would just like to thank the two students who've been involved in this work. It started out with Poonam Kumari, who's as a part of her thesis, and we looked at the low angle regime in this thesis of Sumanti Patra. And essentially, our understanding is that it's the concentrated regions of this enhanced perturbation which is leading to the subband formation and this very unusual behavior in all these systems. And these are some of the references on the topics that I discussed today. And the last one is especially related to the work that I presented today. And thank you all for your attention, and I'd like to.
Thank you, madam, for your wonderful presentation. So we have got few questions. So if you allow, we can start our discussion session.
Sure.
Okay, so the first question: what is the bulk replication in layered solid?
Sure. Went off for a few minutes. Can you hear me?
Yes, we can hear you. Okay, so the first question is: what is the bulk replication in layered solids?
Is the what? Sorry.
What is the bulk? What is the bulk replication in layered solids? I can add the question in the screen. You can see also the screen.
Oh, replication layered solids. Okay, in bulk because you just have these, you have only two. So this is big here. It's only because you have these different, small rotation. Just a minute. Okay, where is that? Yeah. So at these small rotation angles, what I have is I have these regions which have this particular. I have some regions which have like atom on atom type stacking, like the bulk, and some other regions where I have like this displaced stacking, unit cells over here. Okay, so so that's the reason why in these structures, I will. What you can see is that three different patches. Whereas in this, where I went to here, I do not see any particular. I do not see any, but I can't associate any region with any of those high symmetry stacking. because by the time I move from one atom to the next in this large unit cell, it's rotated away. Okay.
Okay. So we have got another question. So the next question is,
Yeah.
do the angle resolved photoemission studies of d electrons in layered solid give us the insight about the band symmetries?
They would, I mean, in the sense, uh, is it, yeah, they would give us some insights about, basically, we would compare it with existing, with the calculations and try to understand what is the character, and we can also determine the nature of the bands which are contributing to the, okay, we can understand the nature of the bands, whether it's which kind of states which are emerging, and by probably by I would say by comparing with with calculations, you could also understand, if you could understand the nature of the symmetries, and you could understand the character of the bands by using particularly polarized lights. You could understand whether it's, involving uh, planar orbitals or out of plane orbitals, and so on and so forth. Yeah.
Okay,
Are
thank
you
you,
able
sir.
to hear me? Yeah.
Yes, 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 we can hear you. So this is another question. So what is the meaning of dispersion-less band?
Oh, there is no dispersion. Like, for instance, absolutely flat. So if I went to some picture like this, um, wait, where is, I mean, okay, here is my dispersion less. One second. Why is it not? Yeah. So you can see that this is what I've been plotting my band structure as: E as a function, energy as a function of the momentum vector. And what you can see is over here, you have a band which is, almost dispersionless. Basically, its energy changes by just 19 MeV here. Okay. And that's it. That is its width. So at K, its energy is almost remaining constant. That's what I mean by a dispersionless band.
Okay, so madam, this may be the last question. What are the
Sure.
interlayer properties of electrons in layered metals?
Means I don't understand what exactly. I mean, basically, if you thought of a tight binding model, okay, or you're just what one is talking about is the electron hopping from from this. Okay, what I'm trying to, if I show it pictorially, it's the, come back to some picture. Just a minute. Okay, if I showed you this particular picture, it's the electron hopping from this atom to this atom. Bring the at one point on the one, and therefore there's a finite matrix. Okay, that is what we call the hopping matrix, hopping strength. So the same thing from this, from this, the electron is hopping to the nearest, and it finds the next by the hopping interaction strength, interlayer hopping strength. Yeah.
Thank you, madam, for your wonderful presentation and discussion session. So I hope our students and the viewers have learned a lot of things about the building solids layer by layer. And our main aim is to motivate and encourage our students. I think some of our students may be motivated by your lecture. So thanks again for giving us this opportunity to arrange such an important webinar. Bye for today, madam. Have a nice day.
Yeah. Thank you very much. Yeah. Thank you.
It's
Bye.
my pleasure. Bye. See you.